Javal was a prolific designer of optical devices and was a monumental figure in 19th century ophthalmology. His eponymous Javal-Schiotz ophthalmometer ushered in a new era of instrumentation. This father of orthoptics had an infinite capacity for work and was not only an ophthalmologist but a legislator, journalist and congressman. Javal was born in Paris on May 3, 1839, into a wealthy Jewish family. His father was a successful businessman and his mother an Austrian of noble birth. In a centenary tribute to Javal, his character was described as a practical idealist, zealous in work, simple in taste, and easy of access. Although initially interested in medicine, his family encouraged him to study mining in the hopes that he would one day take over the family's coal mining business. At the age of 23 and having spent only 1 year in the mining industry, Javal enrolled at medical school at the University of Paris. He graduated in 1868 and travelled to Berlin to study under von Graefe. He subsequently returned to serve as a medical officer during the Franco-Prussian War. He later became the first director of the Laboratory of Ophthalmology at the University of Paris. He preferred non-surgical approaches and would refer all such cases to colleagues. He had a preference for the use of the stereoscope to build fusional ranges for his patients with strabismus. He had many famous students, including Schiotz, with whom he collaborated on his ophthalmometer, and Schoening, with whom he worked on many optics and astigmatism problems. Outside of medicine, he was preoccupied with social reform issues of the day, including education and poverty, and represented his community in Congress for around 20 years. Javal's vision began to deteriorate at age 45 from glaucoma, and he was completely blind by the summer of 1900. He continued to advocate for the blind and wrote a book discussing practical adaptations to blindness. Here he can be seen getting his morning exercise on a tandem bicycle. He passed away from stomach cancer in January of 1907. Javal made many important contributions to ophthalmology, including the Javal grid, a test for simultaneous binocular vision and for detecting ocular suppression. He also created his own version of the stereoscope, is credited with coining the term saccades, and was the first to recognise that amblyopia could be the result of, and not necessarily the cause of, strabismus. Perhaps his most famous invention is the Javal-Schiotz ophthalmometer, a modification of the von Helmholtz ophthalmometer, developed with Schiotz for use in their clinical laboratory. Before we can understand Javal's instrument, we need an understanding of the optical principles of keratometry. All keratometers estimate the radius of curvature in the central part of the anterior corneal surface. They do this in a non-contact manner. This is achieved by measuring the first Purkinje image of a target, or Maya, reflected by the corneal surface. Keratometers treat the front surface of the cornea as a spherical mirror. From this assumption, we can obtain its radius of curvature, and from this, indirect calculation of the keratometric power. Keratometers provide the principal meridians of the eye, maximum and minimum, which are 90 degrees apart in a normal eye. Today, keratometers are frequently used for contact lens fitting and preoperative workup for cataract surgery. The first description of corneal curvature was made by Christopher Scheiner in 1619. He observed a small reflection of a window on the anterior corneal surface of a man sitting opposite a window. This image is today called the first Purkinje image, or the Maya. A simple principle of reflection is exploited today in keratometry, but the tear film is used as a spherical convex mirror. Only the central axial zone of the cornea may be taken to be a sphere. For this reason, keratometers only take measurements from the central 3 mm. This ray diagram depicts ray tracing in convex mirrors. The magnification produced by this tear film mirror is the ratio of the image size I to the object size O. This I to O ratio is proportional to the ratio of the distance of the image V and the object U from the mirror. Thus, I over O is equal to V over U. In most instruments, working distance U is large relative to the corneal radius of curvature, R, and we can therefore assume that the image I is located at the focal point. The focal point is halfway between the centre of curvature of the mirror C and the mirror itself. On that assumption, V is equal to half the radius of curvature of the mirror. V equals R over 2. The radius of curvature of the anterior cornea may be calculated as such. 3 of these variables are known, the 4th can be calculated using the formula. It can thus be seen that as the cornea becomes steeper and its radius of curvature R becomes smaller, the image I also becomes smaller. All keratometers hold the focal distance of the viewing telescope U constant. The 2 types of keratometers are the Helmholtz keratometer, where the object size is fixed and the image size is adjusted. Conversely, the Javal-Schiotz keratometer uses varied object size to achieve a standard image size. To convert the radius into dioptric power for a two-sided refracting element such as the cornea, we ideally need to know the curvature of the anterior and posterior surfaces and the refractive indices of the cornea and media on either side. Direct measurements of the corneal posterior surface is difficult, and the keratometer can only provide information on the anterior surface. To get around this, we estimate the posterior corneal curvature based on the curvature of the anterior surface by assuming they relate to each other in a constant factor. The keratometric index of refraction takes into account the negative refractive power of the posterior surface, which is about -5 diopters. With this in mind, the refractive index of tears, which is 1.336, was standardized to 1.3375 in the keratometric equation, such that a radius of curvature of 7.5 mm corresponds to 45 diopters. The optical power of the central cornea is thus given by a difference in refractive indices of tears and air divided by the radius of curvature of the anterior corneal surface. Javal and Schiotz simplified the Helmholtz ophthalmometer in 1881 to create a practical clinical tool to measure corneal astigmatism. It rapidly achieved wide acceptance and remains one of the most common types of keratometer today. The Javal-Schiotz keratometer is an example of a two-position keratometer. It uses a pair of Myers as the object. These are mounted on an arc that extends from each side of the telescope so that they can be moved synchronously and rotated about an axis of the telescope. In this way, measurements can be taken in any meridian. The object size O is taken from the space AB between the Myers. Moving the Myers apart increases the object size, while moving them together decreases it. Myers consists of coloured windows illuminated by small lamps. One Meyer has a green filter and is stepped, the other is rectangular with a red filter. Here is a schematic of the Javal-Schiotz keratometer. The Myers are adjusted in such a way that they focus the image onto the centre of the cornea. Magnification of the Meyer is achieved by the objective lens, the blue lens in our diagram, and a doubling prism, the pink rectangle. In optics, an objective lens is essentially a high-powered magnifying glass with a short focal length to maximise collection of light from the source, in our case the image eye. The doubling prism overcomes the small jittery motions of the normal eye. This problem is solved by splitting the image into two and calibrating the separation with a radius of curvature. The doubling device is usually a Wollaston prism such as quartz, a double refracting prism that splits a single beam of incident light into two polarised beams. Two rectangular quartz crystals are usually cemented together. The crystals are placed at 90 degrees to ensure outgoing beams are separated by a fixed angle. The Javal-Schiotz keratometer produces a fixed amount of doubling. The image is then observed through the ocular. Degradation of the corneal surface is another common patient factor affecting image quality. Keratometers use the air-tear interface as the reflection site, and errors can arise in patients with dry eyes. Asking the patient to blink just before the readings are taken will refresh the tear film and provide a smooth optical surface. If keratometry is being performed as part of cataract biometry, keratometric measurements should be taken first to avoid disturbing the ocular surface with the ultrasound probe. Furthermore, the keratometer also assumes the cornea to be symmetrical, which may not be the case following refractive surgery or in keratoconus. The original Javal-Schiotz ophthalmometers used two candles to front illuminate each Meyer. Later designs use electric lamps for illumination. Today, the illumination system is located inferiorly in the apparatus, between the Meyers and the objective lens. The first image here depicts the patient's view, and the second is the examiner's view through the instrument eyepiece. When images meet, the Meyer separation scale can be read to determine the corneal radius and dioptric power. The optical system is then rotated 90 degrees to determine the second meridian. When corneal astigmatism is present, the Meyers may overlap or be too far apart. Each step of the Meyer corresponds to 1 diopter of corneal power. When oblique astigmatism is present, the central bisecting lines of the image are not aligned. In this case, simply rotate the instrument until they are. Javal made incredibly important contributions to the field of ophthalmology. He published profusely as a young adult and in later years ran a highly respected and productive ophthalmology lab. He generated new insights into strabismus and astigmatism and developed instruments including his famous ophthalmometers still in common use today.